Morning.
Morning.
So, today I'd like to continue our discussion of carbonyl chemistry. And remember, we've now started on this second aspect of carbonyl chemistry, reactivity of the alpha carbon. And so for this lecture and then the following two lectures, we're going to continue to be developing this idea. So today we're going to discuss a few more reactions of enols and enolates, and what we do today is going to set the stage for chapter 24. So we'll be finishing up chapter 23 and setting the stage for chapter 24, which really gets into some absolutely beautiful and profound carbonyl chemistry with the aldol reaction and the Claisen reaction. So I wanted to start out just by coming back to enols and enolates. And so here's sort of a generic structure of an enol. Maybe I'll draw in a couple of lone pairs of electrons just so we get a nice resonance structure. And here's a generic structure of an enolate. And of course, enols we've already talked about in the sense that we've said they're not stable species that you can isolate in general, that while some compounds are largely enolic, most carbonyl compounds have only a tiny percentage of enol that forms at any given moment, and it's transiently formed and it's acid or base catalyzed. Enolates, on the other hand, we've already seen with, say, LDA chemistry, that you can go ahead and quantitatively convert a ketone to an enolate by treatment with LDA. So if I wanted to make some generalizations, because we're going to be talking about principles of reactivity both today and then in the next two lectures, if I wanted to talk about some generalizations, I'd say that enols are more reactive than alkenes. In other words, we've seen acid-promoted reactions of enols. We were seeing tautomerization, and these reactions occur with very mild acid. You've seen reactions of alkenes. So for example, you've seen treatment of an alkene like isobutylene with aqueous sulfuric acid to form a hydrate, to form an alcohol, the hydration, the addition of water across an alkene by way of a carbocation. That requires very strong acid typically. Typically, you're talking about taking an alkene with a concentrated sulfuric acid solution. Whereas in the chemistry of enols with electrophiles, because you're getting an oxocarbenium ion intermediate, not a regular carbocation that really is suffering from a lack of a complete octet, you have a much greater propensity to react with electrophiles. So if I wanted to sort of characterize an enol, I'd say it reacts with very reactive electrophiles. But again, that's sort of a relative term in the sense that alkenes react with even or require even more reactive electrophiles to react. So we're going to see reaction with halogen. I'll just write this as X2 to indicate really chlorine, bromine, or iodine. Fluorine's always in a sort of special category. It'll react, but it'll react with absolutely everything because the fluorine, every position in the molecule because the fluorine-hydrogen bond is so strong. So alkenes also react with halogens, but now where you start to see enhanced reactivity is, for example, protonated carbonyls. Typically, if you had a ketone in acid, sure, you generate a protonated carbonyl, transiently, but it's not going to react with a typical alkene under typical conditions. Again, I can give you exceptions to that. Whereas this is going to be the basis for what we'll see in the next lecture on the acid-catalyzed aldol reaction. Although I won't show examples, we're not going to talk in detail about the chemistry. I'll give you one sort of comparison. If we talk about an iminium ion, so the sort of iminium ion intermediate we talked about before, these two react with enols in what's called the Mannich reaction. Remember how I've talked about the aldol, I've talked about carbon-oxygen double bonds and said in many ways carbon-nitrogen double bonds are very similar in their reactivity. So an imine is very similar to a ketone in its reactivity, just a little bit less so because nitrogen's a little bit less electrophilic, a little bit less electronegative. An iminium ion is very similar to a protonated ketone, and so there's this manifold of reactivity, whereas a typical alkene wouldn't, under usual conditions, react with an iminium ion or a protonated ketone. Now, coming to enolates, since we now, here, why is this more reactive? You've got the oxygen pushing electron density into the enol double bond. So you're donating in electron density. It's more electron rich than a regular alkene. And along the same lines, as I said, when it reacts with electrophiles, the carbocation that forms gets extra stabilization from that oxygen. Well, enolates are even more nucleophilic. In other words, they're even more reactive toward electrophiles. So in addition to things that are only moderately electrophilic and or in addition to things that are very reactive electrophiles, enolates can react with moderately reactive electrophiles. So sure, an enolate will react with a halogen because halogens are good electrophiles, but you can also react with things like alkyl halides in SN2 reactions. We saw this before when we talked about the direct alkylation of enolates, taking a ketone, converting it to the enolate with LDA, and then alkylating it, say, with methyl iodide, as we saw in the last lecture. Ketones and aldehydes are a lot less reactive than protonated ketones and aldehydes. And so these two react with an enolate because an enolate is so much more electron rich, so much more nucleophilic. And again, this is chemistry we'll be picking up on in chapter 24 when we start to talk about the aldol reaction. And then similarly, under the right condition, esters, which are even a little less reactive than ketones and a good bit less reactive than aldehydes, also under the right conditions can react with enolates. All right, where I'd like to begin today's discussion then is to talk about reactions with halogens, so specifically the alpha halogenation of ketones and aldehydes. And so in sort of a very generic equation, if I have some sort of ketone or aldehyde, obviously with alpha protons, and we treat it with some halogen, and as I said before, we're really talking chlorine, bromine, or iodine, with fluorine sort of being in a special class of its own in reactivity, you react to get an alpha haloketone or aldehyde. And organic chemists are terribly bad at balancing equations, but also hydrogen halide. And this is important. The reaction in the acid manifold, in the enol manifold, is catalyzed by acid. So I'll write reaction proceeds by the enol Now, if a reaction produces its own catalyst, that means the reaction is also autocatalytic, self-catalytic. It catalyzes itself. Autocatalytic reactions can be a lot of fun because often that means you mix the reactants and they seem to just be sitting there. And then they start to react because you have a little bit of the acid around, or because it can go by an uncatalyzed manifold, or you always have some enol present. So it generates more catalyst, which goes faster and faster and faster. And if you don't have it, and if it's exothermic, it can take off because with more heat that it's producing, it'll go even faster and produce more catalysts, which is one of the reasons why when you're in the laboratory, you're so often running reactions in solvent rather than mixing chemicals directly together. The solvent dissipates the heat. It can boil with a reflux condenser and be condensed and come back and take away heat. Anyway, so for example, I'll write a real example of a reaction. If you take cyclohexanone and treat it with chlorine in water, so often when we're writing synthetic reactions, we'll just write reagent over the arrow and sometimes solvent below the arrow. Then you get the alpha chlorocyclohexanone, 2-chlorocyclohexanone. And I'll write plus HCl, although I'll remind us that when we're in water, of course, you don't have HCl in water. When you're in methanol, you don't have HCl in methanol because you protonate your solvent, you protonate your water to give hydronium ion. HCl is a much stronger acid, it's negative pK of -7 or thereabouts. It's a much stronger acid than the conjugate acid of water, the hydronium ion, and ditto for methanol. So if I really want to write things out here, I'd say plus H3O plus and Cl minus. So let's take a look at how this reaction occurs. All right, we talked about enolization last time, so I'm only going to write out a sort of abbreviated mechanism. I will not write every last lone pair of electrons. In writing my mechanism, I will not write every step in gory detail. So for example, our ketone plus H3O plus is going to be in equilibrium with the protonated ketone and water. Water can pull off the alpha proton. You've seen all of this mechanistically, and so you have this equilibrium to form the enol. Remember that equilibrium lies way, way to the left, so you only have a teeny tiny percentage of enol, only a fraction of a percent of enol at equilibrium. But that's okay because it's going to keep getting regenerated under the acid catalysis as soon as you use it up. So our enol is nucleophilic on the alpha carbon. Here's our chlorine. I won't draw all the lone pairs of electrons on the chlorine, but electrons flow from the oxygen down. They flow from the double bond to the chlorine. We push electron, break the chlorine-chlorine bond, push electrons onto chlorine, and now you get the alpha chloro compound. And I'm going to remind us here that we have a hydrogen at the alpha position just to help us keep track. So I suppose if you wanted to, you could go ahead and put in a hydrogen here. I just don't want to lose track of what's connected to what carbon. The other thing that's produced is chloride anion, like so. And again, I'm not going to write in every lone pair of electrons. Then in the next step, we're going to just lose our proton. And remember, technically, although chloride's a base, if you're in water, a reaction like this would be done literally bubbling chlorine into water, bubbling chlorine from a gas tank into water to make chlorine water. And so if you're in water, the strongest base that you'll have is water under acidic conditions. And so we can envision water coming along with its lone pair of electrons, pulling off a proton, putting them back, putting electrons back onto the protonated oxygen. And I guess here, if I want to be a good person, actually, I am going to say this one is essentially irreversible because basically once you form that chlorine bond, you are, for all intents and purposes, not breaking it again. And so our overall outcome is now you have the alpha chloroketone plus H3O plus. Question?
Can CO2 add like anti to the alkene, like in a chlorine bridge sort of thing?
Ah, okay, good question. So the question that's being asked is we have chlorine here and we have alkene, and we've learned that with chlorine, you can add across a double bond like so. Don't worry about your stereochemistry right now. So you've learned that you can do that. And indeed, it's possible that chlorine, because you think of it as stepwise, you have that oxocarbenium ion, you can write the other resonance structure just like you do with an alkene. You'd say, well, chloride could come in and intercept. And indeed it could, and indeed it can. Do we have any ideas about what this compound would do?
Kick out the good leaving group.
Kick out the good leaving group. And we're actually going to come back. So indeed, so sure, chlorine could add as an equilibrium, and you're never going to have a stable adduct of chlorine into the carbonyl, whether it's as an oxyanion or as a hydroxychloro compound. We're going to come back to this idea when we talk about the haliform reaction, which is a really weird reaction. We'll talk about that in a moment. But talk about it in a little bit. But you never have a stable adduct. There's like one exception. Iodide can add into acetone and certain ketones and form a stable oxyanion adduct. Your book doesn't mention it. It's sort of the exception. They say it never occurs. I can give you the one exception. Question?
If the two carbons next to the covalent carbons are not equivalent, is there a selectivity between them?
Ah, okay. These two carbons, the ones next to it, alpha on either side, in this case, are equivalent. And so you basically chlorinate once. If I keep pushing it and letting it go longer, yeah, it'll chlorinate again. But this reaction pretty much, because the chlorine is electron withdrawing, can stop very nicely after addition of one chlorine. I'll show you an example in a moment where we have two different ones, and we'll talk about the regiochemistry. How does the double bond form in the first step over here?
No, the next step. Yeah, there. Like, how does that get there?
How does that get there? In other words, how do we get from here to here? Okay, so here are your protons. Water's your strongest base. You can think of the water, whoops, as pulling off a proton. Electrons flow in, electrons flow onto the oxygen. You're welcome. So that's acid catalyzed enol formation. All right. So let us talk now about some other cases. I'll give you a couple of examples. Now, one thing that I've done is broke with your textbook, and I know you get bent out of shape when I tell you the way things really work, and your textbook gives you slightly simplified answers. So I didn't draw any catalytic acid in there. And in reality, you really don't need it. Now, I'll tell you the secret about chlorine. Chlorine in water. So not only do you have some enol to get things going, but chlorine actually disproportionates in water, giving HCl, hydrochloric acid, and HOCl, hypochlorous acid. So a solution of chlorine water is always acidic. So you don't need to add any acid to get things going. I'll give you an example straight from your textbook if it gets you less bent out of shape. We'll take acetone, treat it with bromine, and as I said, this really works for all of the three regular halogens. Take acetone, treat it with bromine and acetic acid, and you'll get alpha bromoacetone plus HBr. And by the way, HBr and acetic acid is super, super acidic because acetic acid is less basic than water. So HBr and acetic acid is really strong. You're getting a lot more acidity than that negative 1.7 of H3O plus. Anyway, I'll give you another example and come back to the question of regiochemistry. One of the things that's cool about this reaction is the rate determining step is the enolization. As soon as you form enol, it's consumed by your halogen. And it's irreversible, hence my writing my arrow like that. So the enol that forms more quickly is the less substituted enol. We talked before about enolates, and we described kinetic enolates, the less substituted enolate, and thermodynamic enolate, the one that's more thermodynamically stable, the more substituted enolate. Well, it's kind of the same with enols. So when you do have two different groups, like an isopropyl group and a methyl group, then you end up going at the less substituted position. And again, this chemistry works in a variety of solvents, so I'll just give you another one, bromine in methanol. You notice all of these are protic solvents. Water, acetic acid, methanol. Typically, those are the solvents that promote enolization, and so those are the solvents typically one would do this chemistry in. So then we go through the more kinetically favorable enol, and as soon as that enol forms, it's consumed. We get the less substituted compound. Don't get too bent out of shape over these details, as in so much of the chemistry I can give you, there are many, many layers, and it gets deeper and richer, and you can go on and on with it. But I wanted to give us a flavor mechanistically and give us a flavor synthetically. Alpha halocarbonyl compounds are really cool. Your textbook talks a little bit about their reactivity. They're really good alkylating agents in SN2 alkylation, kind of like allylic and benzylic halides, which are more reactive toward SN2 alkylation, toward SN2 reaction than a standard alkylating agent. has to do with the orbitals on the carbonyl or the orbitals of the benzyl or allyl group. Anyway, your textbook gives you some nice examples, including talking about synthesizing LSD. All right. What I'd like to do now is to talk about alpha halogenation promoted by base. I'm not saying catalyzed because you'll see when I balance my equation that we use up a whole molar equivalent of base. Synthetically, this is a less useful reaction. And remember, organic chemists tend to be control freaks. We like to control reactions and make them do what we want to do. Synthetically, often enolate chemistry ends up being a little less controlled in the halogen manifold, in the halogenation manifold. So let me start with a simple example, which is controlled. And I'm sort of writing some of these examples around your textbook just to keep things in line with this and to illustrate a few principles of reactivity. So let's imagine that we have this phenyl ketone. So we have one alpha proton, and we have a source of base, so we can form the enolate in an equilibrium reaction. Remember, the pK of a typical ketone is about 20. This will be a little more acidic. But generally, that means since water, the pKa for water deprotonating is 15.7, you're going to have an equilibrium reaction. Anyway, plus bromine. And so very much like the other chemistry we were talking about, you're going to end up alpha brominating. And if I write a balanced equation, you'll see that the other products of this reaction are plus bromide ion and plus water. So you notice we've actually consumed a molar equivalent of hydroxide in the reaction. So the chemistry's very similar. The enolate is nucleophilic. The enolate is even more nucleophilic. And again, I'll skip over the curved arrow mechanism for forming the enolate. It's just pulling off the alpha proton and pushing electrons up onto the oxygen. So I'll just write it in shorthand as OH minus over the arrow to give us the corresponding enolate. And now we have our bromine, and again, I'll write things in a little bit of shorthand, writing the bromine over the arrow and skipping writing every bloody last lone pair of electrons. Electrons flow down from the oxygen to give us our carbonyl back, and over and from the double bond to the bromine, and push electrons onto the bromine to give rise to the alpha bromoketone. Plus bromide. And remember, if you're uncomfortable with all of these arrows moving at once, remember that picture in your mind of the two resonance structures of the enolate, the one with the negative charge on the oxygen and the other with the negative charge on the carbon. And I said I'll usually just keep one in my mind, and it'll be the more important, the bigger contributing resonance structure, this resonance structure. But what I'm really doing with this arrow and moving the electrons from the double bond, of course, is just the mental process of getting to that other resonance structure. So if you're uncomfortable with that, just think about the resonance structure like so. And it certainly is more intuitive, but Johnny probably, for example, would never write this as the attacking resonance structure, just because we tend to think about the more important resonance structure. Question?
If we run out of OH minus, would bromine minus deprotonate hydrogens?
Would bromine minus deprotonate? Another good question. In general, equilibria tend to be active, tend to be significant within about 10 pKa units. HBr, very acidic, Conjugate acid of bromide, about -8, -9, somewhere around there. Bromide's not going to deprotonate significantly. Water, pKa of the conjugate acid, -1.7, not going to deprotonate significantly. So if you really ran out of hydroxide, we could slip into the acid catalyzed manifold. If I tried to play a trick on this chemistry and used half an equivalent of hydroxide and a full molar equivalent of bromide, I suppose the first half of the reaction would run in the base promoted manifold, and then as the base was consumed, eventually we'd start going through the enol pathway. I've never tried it. These are good questions. I like this. This is a lot more fun than simply babbling on. And it means your mind is working. And while we're at it, how about next class we all get down more toward the front row? There's no fun in being in the back row. All right. So let's continue with this, because I want to take us to some principles and something that's cool, kind of counterintuitive, no longer super important in terms of analytical chemistry, but nevertheless very cool. All right. Now let's imagine, because I'm going to walk us from something where we have 1 alpha proton to something where we have 2 alpha protons, and then to a compound where we have 3 alpha protons all on the same carbon. So let's imagine we take this same manifold, a base, and you notice, I mean, remember how I make this point. You can't go to the stockroom and get a bottle of hydroxide. They'll look at you funny. Well, which hydroxide do you want? Potassium hydroxide, sodium hydroxide. Usually organic chemists will use one of those two. Sodium is common. All right, so I'll take sodium hydroxide and bromine, and I'll indicate excess. All right, I'm going to do it. I'll write excess rather than the word excess. All right. And I'll probably keep doing that. I think your textbook writes excess, E-X-C-E-S-S. We also, in the laboratory, when our gas tanks get empty from nitrogen, we run reactions under them, write MT on the gas tank in chalk. All right. So we get the dibromo compound. Now, the real thing I want to make is, oh, don't be quiet. Make some noise. Come on. The real thing I want to say is the reaction doesn't stop at the monobromo compound. In other words, what I'm saying is if I wanted to make the monobromo compound by this route, I'd be in trouble. If I wanted to make the monobromo compound, we could go in the acid catalyzed manifold. But if I wanted to use the base catalyzed manifold, I'd be in trouble. The problem is bromine's electron withdrawing, and so once you put one bromine on there, once that enolate has reacted once, and we get a bromine on there, now this proton's more acidic. And so you get this competition. Now you've got this molecule, because partway through the reaction, you've got this molecule with 2 protons that are less acidic, and then the molecule with the bromine next to the proton, making it more acidic. So if I wanted to be a troublemaker and say, go ahead and use one equivalent, so I'll write NaOH Br2, one equivalent, EQUIV, meaning equivalent, and see what happened, then I'd end up with a mixture of products. I'd end up with some of the dibromo. I haven't done this myself, but it'd be cool to monitor by NMR, because you'd see peaks for all of these. Some of the unreacted starting material, you'd probably see some of the monobromo in there as well. And that's fine, it's cool, it's okay, but remember what I said before about organic chemists being control freaks. Typically, we want to take a reactant and convert it to a single product. And so from the point of view of carrying out a synthetic reaction, it's not so useful, it's not so helpful to be able to get a mixture of, or to not be able to get a single product. Better to do it in the acid-catalyzed manifold. All right, so where all this is leading is to some weird and funky chemistry. So let's take the example now where we have 3 alpha protons. So instead of propiophenone or isobutyrophenone, the first one we had, we'll take acetophenone. And let's make our life simple. We'll treat this with sodium hydroxide and bromine, and again, I'll write XS. And now what's really wild is we break a carbon-carbon bond. We get the carboxylate and CHBr3, which is called bromoform. And this reaction is general. It works with all 3 of the main halogens, chlorine, bromine, and iodine, all the important ones. And so this is called the haloform reaction. So in other words, I can write it, it's general for methyl ketones, so I can write this sort of in general terms of a methyl ketone drawn sort of generically with Cl2, Br2, or I2. In other words, molecular chlorine, bromine, or iodine, and some base, sodium hydroxide, but again, potassium hydroxide would do just fine, generates RCO- or RCO2-, depending on how you prefer to write it. Either of them is fine, plus CHCl3, chloroform, CHBr3, we already said that's bromoform, so I'll say plus one or the other, or CHI3, iodoform. And historically, this reaction's been used as a chemical test for methyl ketones. Nowadays, if you wanted to take a methyl ketone, well, just take an NMR and okay, you've got a methyl peak and you've got a ketone in the IR, and the methyl peak's at about 2 parts per million. You say I have a methyl ketone. But historically, this was used as a test. And typically it was done with iodine, because iodoform is really cool. It's a yellow organic compound. So you take a methyl ketone like acetone, a drop of it in a test tube with some sodium hydroxide, and you throw in iodine, and this yellow precipitate comes out, which is really cool. So you've got this chemical test, and it only occurs with methyl ketones. Iodoform's also neat. It's got this really neat odor to it. It's got this characteristic smell, very, very pretty. However, the thing that I want, your textbook presents this. This is a reaction that historically I thought, do I really want to teach this to sophomores? It's counterintuitive, and it's actually cool in its counterintuitiveness, and it also is relevant. And so I do think this is worth learning about. All right, so what's going on in this chemistry? We're breaking a carbon-carbon bond. So there's something weird going on here. So I'm going to start, we'll do this sort of on our generic methyl ketone, like so. And I'll say as above. By as above, of course, I mean form the enolate, alpha halogenate, form the enolate again, alpha halogenate again, form the enolate once again, alpha halogenate once again. And so at this point, we have the trihalomethyl ketone. And this is unstable to base. And that's really the key. It's unstable under the reaction conditions. It breaks down. We've now put 3 electron withdrawing halogens on carbon. Even though it's an alkyl carbon, it's getting to be a very unusual alkyl carbon. It's rendering, by pulling electron density away from the carbonyl, it's rendering the carbonyl more electrophilic, and you've got hydroxide present. So, here's our hydroxide. Hydroxide can add in, I'll put in a few electrons and try to be a good person. Hydroxide now adds into this extra electrophilic carbon. Now here's where things get fun. And I'll only draw the lone pairs that we need just to prevent us from going crazy here. All right, so at this point we formed a tetrahedral intermediate. But what's special here is that that trihalomethyl group is electron withdrawing. Unlike, say, a methyl group or an alkyl group in general, it can stabilize electron density. So here's the big surprise. Electrons come in and they push it out like a leaving group because, indeed, it is a leaving group in this particular context. So electrons come back. We go ahead. We end up with a carboxylic acid. And again, I'm drawing an abbreviated mechanism. I'm not putting in every gosh darn lone pair of electrons. Our whoops. And here's the kicker, a carbanion. We don't normally see carbanions. You see acetylide anion, but normally, I mean, we see a Grignard. I said a Grignard's like a carbanion, but you really have a covalent bond to the metal. You can just think of it as being like a carbanion because the metal's electropositive. Organolithium reagents, same thing. An organolithium, like butyllithium, is like a butyl anion, but it's not really a butyl anion. But here we can kick out a carbanion. There's something special. So I'm going to write exclamation point just to bring home the point. And of course, the carbanion is still basic, so it can pick up a proton. The carboxylic acid's the most acidic thing around. And so we have the carboxylic acid plus our haloform. But we're dancing around this very uncomfortable step here. We're dancing around this fact that I've just kicked out a carbon with a negative charge on this. Now, you've seen this before. You've seen this before. You've seen this in cyanohydrin chemistry, where we know that we can form a cyanohydrin, but we also know under basic conditions the cyanohydrin formation is reversible. And so in cyanohydrin formation, we learned it forward and backward. We encountered it on a quiz. We became comfortable with the idea of kicking out cyanide anion and getting a carbonyl back. And again, I'm just drawing in the relevant lone pairs of electrons. And the key on this, of course, was that, well, cyanide, yeah, it's a negative charge on carbon, but it's special. I mean, you can buy a bottle of sodium cyanide. HCN, right? We always talk about how stable an anion is by thinking about the pKa of the conjugate acid. HCN has a pKa of about 7. 9. So what's going on here in our haliform reaction? Well, chloroform has a pK of about 25. Your textbook uses that number. That's the number I use too. So when we kick out the trichloromethyl anion, it's not like a carbanion. Remember, methane is 50. This is much more like a stabilized carbanion. Not as good as cyanide. I was curious because I didn't have the numbers at my fingertips. I wouldn't expect you to either. But the pK for bromoform is about 23 off of at least one source. And iodoform, iodine is more polarizable than chlorine, even though it's less electronegative. That means it can better stabilize the, I'll use a little tilde there to mean approximately, can better stabilize the negative charge, pK of 14. So the iodoform reaction, the one that you can do in a test tube, really, really works very easily because basically you're kicking out something that's kind of like an anion and cyanohydrin formation. Now, what's cool to me about this chemistry here, we always calibrate ourselves. I've emphasized this idea of pKa and what are markers to have in your head for various values. I said a factor of 10 pKa units is sort of my weighting on whether an equilibrium occurs to any significant extent. So you can take away that for kicking out an anion out of a carbonyl, that 25 sort of is that teetering edge point. Now this is going to come back in chapter 24 when we discuss the Claisen reaction, but more specifically when we discuss its mechanistic reverse. The Claisen reaction involves an ester enolate adding to a carbonyl. The mechanistic reverse involves kicking out an ester enolate. It's called the retroclaisen. It involves kicking out an ester enolate. Remember that number I said keep in your head, 25 for an ester enolate? So that's sort of right at the same value of chloroform. And so I think the haliform reaction provides us with this very nice calibration point for breaking carbon-carbon bonds. I saw a question there.
If you had a ketone and you did the same reaction in the basic condition, would it add only to one side? Or?
Ketone primarily would, yeah, one side. I'm not sure how clean it would go. I'm pretty sure you would get it clean on the less substituted side under basic conditions. So yeah, I'm pretty sure, because the kinetic enol, remember this reaction is rate determining in enol formation or enolate formation. So you form that kinetic enol or the kinetic enolate, it goes, now it's even more acidified, so it goes at that position again. So I think the answer is yeah. If we took that other one of the isopropyl methyl example that I was showing you before, and tried it under these conditions, would you get all isobutyric acid, or would you get some bromoisobutyric acid, a little bit? I don't know for sure. We could try it literally in the lab. All right, so that kind of brings me to what I wanted to say about halogenation, and now I wanted to start talking about some more anion chemistry, and really this is going to set the stage for the next chapter, but it's also some very cool chemistry in its own, and this is older enolate alkylation chemistry. I'm going to present to us two reactions. One of them is called the acetoacetic ester synthesis, and one of them is called the malonic ester synthesis. The acetoacetic ester synthesis is a synthesis of methyl ketones. The malonic ester synthesis is a synthesis of carboxylic acids. They're both really useful reactions. They can be done on a bucket scale, literally, to make kilograms of compound. Most of the LDA chemistry we were talking about, sort of fussy, you do it in a little flask with a little bit of butyllithium, making 10 millimoles or 100 millimoles of compound, maybe a mole if you're lucky. But this is bucket chemistry. All right, I want to lay the groundwork of this, and I want to come back to the two numbers I told you before. So I said if you want to keep two numbers in your head for pKa's, the numbers you can keep are pKa of 20, and this is sort of a generic ketone. So remember, I'm writing a generic structure here, say 20 for generic ketone. Acetone, the specific example here, happens to be 19, but that's not so important. Basically figure 20. And remember I said for an aldehyde, yeah, it's a little less than 20. If you want to keep another number in your head, keep 17. If you can only fit a certain number of numbers in your head, just keep 20 for all of them. All right, ester, about 25. So we'll use a little tilde here to mean about. All right, what I want to show you now is what happens if we start to have two carbonyl groups. And it shouldn't surprise us that if we have two carbonyl groups, the corresponding enolate is going to be more stable. In other words, the ketone with two ketone groups is going to be more acidic. The ester with two ester groups flanking a hydrogen is going to be more acidic. So this compound here, often called acetylacetone, yeah, if you want to get the IUPAC name, you can call it 2,4-pentane-dione. Its nickname, its common name is acetylacetone, has a pKa of about 9. If you have one ketone and one ester, probably think it's going to be a little less acidic. pKa is about 11 for this one. This one's often referred to as ethyl acetoacetate. Again, if you want to get all IUPAC-y, you can say ethyl 3-oxobutanoate, but a nickname, a common name, is ethyl acetoacetate. And I'll give you an even more common name in just a moment. All right. Two ester groups, even yet a little bit less acidic. Now we're talking about pKa of about 13. This is called diethylmalonate. And it kind of makes sense that diethylmalonate should be a little less acidic. All of these should be more acidic than the monocarbonyl compound. If you want to keep one number in your head, you know, put in 11 if you don't want to, or 10 if you don't want to keep track of all these numbers. But the main point is they're way more acidic than a regular carbonyl compound. All right, what's the reason for this greater acidity? Well, we already talked about how you can write a carbanion-like resonance form for an enolate, but you've got lots and lots of extra stabilization by sticking the negative charge onto oxygen. And so you can write an enolate-like resonance structure. I suppose I'll be a good person here for once. Put in all my lone pairs of electrons. You can write an enolate-like resonance structure or a resonance structure with a negative charge on oxygen. But the cool thing about all three of these 1,3-dicarbonyl compounds is the extra delocalization. Just like a carboxylic acid spreads that negative charge out over 2 oxygen atoms, and so it's more acidic than an alcohol, here we can spread out the negative charge not just on this oxygen, but on the other oxygen. And so it's more acidic than a regular ketone, hence our pKa of 9. Now, what does 9 mean? 9 means that unlike acetone, if I go ahead and treat acetyl-acetone, if I treat 2,4-pentane-dione with sodium hydroxide, I'm going to have an equilibrium that's going to lie to the right to give the corresponding anion, the corresponding enolate. Sodium will be the counterion, and if I want to write a balanced equation, I'll remind us that water balances our equation. So we can quantitatively, we can stoichiometrically make this corresponding enolate because it gets extra resonance stabilization. If I take ethyl acetoacetate, and I treat it with sodium ethoxide, again, I have an equilibrium that lies to the right for generation of the enolate. I'll write the structure where I've enolized the ketone. That's probably the slightly more contributing resonance structure over the one of enolizing the ester. But remember, there are all 3 resonance structures contributing together. Negative charge on this oxygen, negative charge on that oxygen, negative charge on carbon, plus ethanol. And think about it in terms of pKa's. pKa of water, 15.7. pKa of the acetyl-acetone, 7. That equilibrium lies to the right by 7 orders of magnitude. pKa of ethanol, 16 or 17, depending on which number you want to keep in your head. pKa of ethyl acetoacetate, 11. That equilibrium lies to the right by 5 orders of magnitude. I want to use sodium ethoxide for the second one. The first one doesn't matter so much. Why don't I want to use sodium hydroxide for the second one? What does sodium hydroxide do with an ester? Makes it leave, attacks the ester carbonyl, kicks out ethoxide, gives the carboxylic acid. The carboxylic acid swaps a proton. We saponify the ester. Now, if you're thinking, you'll say, well, he keeps saying ethoxide is just like hydroxide in many of its reactions. So can't ethoxide attack here? We had transesterification on the midterm. Sure, it can attack, form a tetrahedral intermediate, kick out ethoxide, you're back where you started. It's this degenerate equilibrium. Sure, it happens. Lots of things happen in carbonyl chemistry. But it doesn't matter. It doesn't make any particular consequence. This is also why I'm choosing to pair sodium ethoxide with ethyl acetoacetate rather than, say, sodium methoxide. Sodium methoxide, of course, unlike hydroxide, won't give you a carboxylic acid. But now we're going to get a mixture of the methyl ester and the ethyl ester as you transesterify. All right, so where all of this is going is to a synthetically useful reaction, which I was hinting at before. The acetoacetic ester synthesis. And I'll put parenthetically of methyl ketones. Because this is a reaction that's useful for making them by the bucket. Now, I hinted that there's another name in addition to ethyl acetoacetate. That name for this compound, in addition to calling it ethyl 3-oxobutanoate, in addition to calling it ethyl acetoacetate, also gets called acetoacetic ester. It's a historical thing. When you go to the lab and you do an extraction, you ask for ether, and it means diethyl ether. When you go to a bar and you ask for a glass of scotch, you say, I'm drinking alcohol, because you're drinking ethyl alcohol, not methyl alcohol. And here, acetoacetic ester means the ethyl ester of acetoacetic acid from historical terms. Let me introduce the reaction, and then we'll talk about the mechanism, because it's cool in addition to being useful. All right, so here's our acetoacetic ester. We'll treat it with sodium ethoxide in ethanol. Very easy to make. You throw a chunk of sodium into ethanol. It fizzes. It doesn't catch fire in ethanol, fortunately. If you throw it into water, it catches fire. You take an alkyl halide, and we're talking about one that's good at SN2 alkyl halides. In other words, not tert-butyl bromide, but something better like ethyl iodide. You can probably get away with isopropyl, but you can't go with tert-butyl because it doesn't do SN2. Finally, we throw in some acid, and we heat this gamish, and out pops a methyl ketone where we now have the R group on it. This sounds kind of abstract, so I want to give us a concrete example. So let's say we take, and then we'll walk through how it occurs. All right. So let's say we take ethyl acetoacetate, we treat it with sodium ethoxide in ethanol. We'll take an alkyl halide. I'll choose propyl bromide. I could use propyl iodide. Bromides are cheaper than iodides. Propyl chloride is, I think, a gas, or it teeters on the border of being a gas. Propyl bromide is a liquid. I can buy it. Alkyl bromides are good at SN2 displacement reactions. And we do an aqueous workup with acid. Acid unspecified, but as I keep saying, you can't go and buy a bottle of H3O+, so we're talking about either HCl or sulfuric acid and water. And the methyl ketone we'll get out of here. We've got a lot of carbons, so I want to help us keep track. That's why I've given us a concrete example. The methyl ketone we get out of here is 2-hexanone. All right, what's going on here? All right, first part, and I'm going to give us an abbreviated mechanism because we've seen a lot of these steps. All right, first part's easy. You have your anion, drawing one of the resonance structures of it, make our lives easier. You want to draw a different one, that's okay too. Electrons flow from our nucleophile, from the alpha carbon to the electrophile. We kick electrons onto bromine in an SN2 displacement. So now we've alkylated with a propyl group. No, I'm not going to balance my equation and show the bromide. We're just getting a flavor of the mechanism. Okay, next step. We treat with acid. Do this aqueous acid. And what is this? It's acid catalyzed ester hydrolysis. We've seen that before. You protonate the carbonyl, water attacks, you kick out, you swap some protons around, you kick out ethanol. All right. So at this point, we have a beta keto acid. What the heck? I'll be a good person. Write ethanol here. But this is the guy that we're going to focus on, the beta keto acid. All right, beta keto acids are special. 1,3-diacids are special. They can undergo decarboxylation, and the mechanism's really cool. Going to write a different conformation of the molecule. This is probably the preferred conformation where the OH group is hydrogen bonded to the carbonyl. All I've done is spin around this bond here. Here's our propyl group. We can move 6 electrons in a ring, like so. And that occurs upon heating. When I push our arrows, let's think about it. What does this mean? We're forming a bond between this oxygen and hydrogen. We're breaking this bond. We're forming a bond between this carbon. We're forming a double bond over here. So we formed carbon dioxide. Guess I'll write a little plus sign. Call this a decarboxylation. That's an OH up there, if you're having trouble seeing. We call this a decarboxylation because we're losing carbon dioxide. So that's kind of intuitive. But this also fits into this broad class of reactions you learned about in 51b. It's a pericyclic reaction. What's the archetypal pericyclic reaction you learned about in 51b? Diels-Alder reaction. This is just like the Diels-Alder reaction, 6 electrons moving in a ring. If you want to get technical, I can call it a retro-Ene reaction. Try that one in one of your lab TAs. They may not have seen that before. But however you want to talk about it, pericyclic reaction, decarboxylation reaction, retro-Ene reaction, something like the Diels-Alder reaction. We've broken a carbon-carbon bond and gotten carbon dioxide. Our ketone undergoes enolization, or, well, keto-enol, I will write tautomerization. And that gives rise to the 2-methyl ketone because, of course, enols aren't stable. All right, so let's just put all of this together, and I'll show you a cool synthetic example, something a little bit different. We're going to have some fun with this. This really is useful chemistry. It's chemistry by the bucket. You can prepare methyl ketones. So we'll take our acetoacetic ester. We'll treat it with our proverbial sodium ethoxide in ethanol. We're going to do a double alkylation. We're going to alkylate once and alkylate again. So I'll take ethyl iodide. Now I'm going to continue. So we've alkylated once, but in your mind's eye, imagine we're now going to treat with some more sodium ethoxide. I'm not going to write it out for you. Picture this in your mind's eye. We treat with some more sodium ethoxide. We again generate the enolate. We repeat, and now just for fun, let's use some methyl iodide, CH3I. Now we carry out an aqueous workup and heat it and decarboxylate in the same way we've done up there. But we've done a double alkylation. We've put on a methyl group and an ethyl group. And so we've used this as a reaction to synthesize 3-methyl-2-pentanone. So that's cool, that's useful. You can synthesize a bunch of methyl ketones by way of this chemistry. All right. This lays the groundwork for the last section that I want to talk about, the malonic ester synthesis. Of carboxylic acids. I already showed you diethyl malonate. That was the one with the 2 carboxylic acids, the 1,3-diacid. Again, the old nickname for it is malonic ester because it's the diethyl ester of malonic acid. And we already said, well, ethyl is sort of the default. So we take our diethyl malonate, also available cheap, like ethyl acetoacetate. I'll talk more about how all of these are formed as we get into the Claisen reaction in chapter 24. So we take our malonic ester, and now we're going to do the same type of chemistry. We're going to first treat with sodium ethoxide in ethanol. We'll then treat with an alkyl halide. Again, we're talking about an alkyl halide that's good at SN2 displacement, so not tert-butyl bromide, but a primary alkyl halide or maybe even a secondary alkyl halide. And finally, we'll carry out an aqueous workup and heat with acid. And the product of this reaction is the corresponding carboxylic acid. Chemistry is very, very similar. Make the enolate, alkylate, hydrolyze the ester groups to the corresponding carboxylic acid, the diacid. Here's our diacid. I guess I'll write it once, sort of normally, so you can see it. And then I'll write it once in a more realistic conformation with an internal hydrogen bond, just like we did in the other case. Again, we're going to push our electrons in a ring, like so. We lose carbon dioxide, just as we did before. We get the enol form of the carboxylic acid. And we tautomerize. All right, where I want to conclude is coming back to the idea of seeing backwards to retrosynthetic analysis. We've seen the acetoacetic ester in the forward synthesis in the forward sense, and that's fine because you'll figure it out for the backward sense. I want to show you this in the backward sense. We already saw in the midterm exam how you can look at an imine and take it apart to the corresponding ketone and amine, to an enamine, and we can do the same thing, to various types of alcohols, and we can do the same thing. So let me give you one more retrosynthetic disconnection. Let me write out a little problem here. Let's say we want to prepare 3-phenyl propanoic acid by the malonic ester synthesis. All right, so we look at this compound, and we look at the chemistry we've seen in the malonic ester synthesis. And we look at the same chemistry we've seen in the acetoacetic ester synthesis, and we say, all right, what are we really doing? We are really forming this bond, the bond between the alpha and beta carbon, by an SN2 reaction. And so in our mind's eye, when we look at 3-phenyl propanoic acid, we look and we say, ah, okay, that's the bond that we're going to make by an SN2 reaction in the malonic ester synthesis. And so we see something in a big piece now. This is what retrosynthetic analysis is all about. This is what seeing that acetone imine and saying, oh, that's the imine from acetone and ethylamine. That's the big site that you get. So we look at this, and now we say, oh, yeah, we're going to form that bond. We're going to use the malonic ester synthesis with a benzyl halide. And you'll just go to your chemical shelves and pick your favorite benzyl halide. We'll go with the bromide. It's nice and reactive. We could go with the chloride, but bromides are a little bit more reactive. So we'll start with our malonic ester. We'll start with our diethyl malonate. We'll treat it with sodium ethoxide and ethanol. See, and this is all pre-LDA chemistry. LDA really came about in the late 1960s. And to me, it was transformative in chemistry because it really meant that you're orchestrating a reaction, no tricks. I have a ketone. I'm going to make an enolate. I'm going to alkylate it. I have an ester. I'm going to make an enolate where I want it. I'm going to alkylate it. Here we have a trick because sodium ethoxide isn't basic enough to quantitatively pull off the proton on ethyl acetate. You have an equilibrium that lies 8 orders of magnitude, 9 orders of magnitude to the left on that reaction. But by going ahead and using the 1,3-dicarbonyl compound with this trick, we're going and saying, yeah, we're going to quantitatively get that enolate, then we're going to alkylate it. So sodium ethoxide and ethanol, benzyl bromide, aqueous acid, that's like sulfuric acid and water, or hydrochloric acid heated up. And we have our phenylpropanoic acid. All right, one last example from your textbook, and I think it's a good one, so I want to show it to you and really think our way through it. For beginning students in organic chemistry, rings can really mess with your mind. And so often when a beginning student sees a cyclic acetal, it's very, very different in their mind than a regular acetal. And of course, being able to break out of that and see beyond that's really valuable. So here's an example. I'm going to say prepare cyclopentane carboxylic acid. And presumably, since we're talking about the malonic ester synthesis, we should be thinking about that. And you look at cyclopentane carboxylic acid, and you say, well, wait a second, we got this ring here. What do we do with this? We learn that we're breaking the alpha-beta bond. Well, here's an alpha-beta bond. Here's an alpha-beta bond. We know we can form two. We saw in the acetoacetic ester synthesis where I used ethyl iodide and methyl iodide that you can do it twice. And you can do it twice here. And if you think about it, what that means, thinking backwards, is it means that we're going to this, but we know we put this in quotes because that's the piece coming from the acetoacetic ester synthesis, and this. And so that becomes the crux, recognizing that we have a dihalobutane. And so now, all we have to do is put this into action in the forward manifold. We start with diethylmalonate. Now the nice thing, the reaction's forgiving. You can throw stuff together. I've been writing step 1, step 2, step 3. You can throw, well, you can't throw the acid together with the base. You'll quench the base. But I can go ahead and throw this bromide with sodium ethoxide in ethanol. And in this gamish, sodium ethoxide is going to react, deprotonate, alkylate, deprotonate again, alkylate. So that's step 1. At that point, we have this stuff. You don't even need to isolate this cyclopentane diester. Now we just take this. I'll just write this with an arrow, H3O plus, delta. We hydrolyze, we decarboxylate, and we get our cyclopentane carboxylic acid all in one fell swoop. And that ends chapter 23. See you on Tuesday.